My name is Anna Ndozo, and this is my Physics 2211 Lab 1. This video is about constant velocity motion. I'm going to be talking about the lab, tracker analysis, a computational model, observed versus predicted comparison, and some conclusions. In this lab, we're going to be trying to observe constant motion, and two things that we need for that are some fundamentals, Newton's first law and second law. Newton's first law is that an object in motion tends to stay in motion, and an object at rest tends to stay in rest. To piggyback off of that, Newton's second law, unless there's a net force acting on a system, there should be no change, or net force equals mass times acceleration. An object should face no acceleration, or will stay at rest, or stay in the same motion, unless there's something acting on it to change that. Momentum is equal times mass velocity, and net forces is equal to change in momentum over time. If there's no net force, there should be no change in momentum, and if there's no change in momentum, there should be no change in velocity. In the bottom left, by deriving those things I just said and moving around variables with equations, that we should see that the final velocity should equal initial velocity. And this is considered the velocity update formula. And we see that acceleration is equal to force divided by mass. Another key equation we're going to be needing to use is the average velocity. We're going to change it around to actually get the position update. As mentioned, the velocity shouldn't be changing, so the change in time and the change in position should be consistent. If it's moving 2 meters away at a rate of 2 meters per second in 2 seconds, it should have moved 4 meters. We have the key concepts that we're going to build off of. What experiment did we do? Our group was told, get a video of an object in constant motion. Our group decided to use an expo marker. Using that video, we'll be provided with a tracker analysis. Using that tracker analysis, we're then going to use a computational model. And then from there, we're going to be conducting the experiment, seeing did things pan out like we wanted, predicted? How did things actually play out? The lab procedure is written now very clearly and plainly, capturing a video of a marker rolling in a straight line with constant speed. Import that video to our tracker application to track the position and marker frame to frame. Take the data from that and put it into some Python glow script code. And they're going to see what model spits out and see whether or not the constant velocity is there in the t seconds or delta t time that we observed it in. We're going to compare the plots, both computational and the experimental data. In the motion, we are going to be acting as if there's no air resistance or any forces of friction acting on the system, or acting as if there is zero net forces once the video is done. And we're only going to be taking into account the x-axis of motion, or horizontal motion. Here we see our video. It's only 0.671 seconds. We treated the initial position to be from where my groupmate's finger left the marker, which got it to its initial velocity, which should be its final velocity, or constant velocity. The shutter speed between frames was 0.033 seconds, which we accessed through the data panel. By using the middle column or the x displacement, we were able to derive that the average velocity, initial velocity, constant velocity, was 0.481 meters per second. The only reason the sign is positive and not negative is because we decided to compute it by flipping the signs. The velocity would be the same, magnitudinally left or right, 0.481. The only difference is the sign. Using those first two columns of the bottom right data from the tracker analysis, we were able to input it into glow script code. This code was accessed from the lab page. We modified it to have the proper starting mass of our marker, which we inputted on the right, the position and velocity that we gained from the video, and also the time frame. Pairing out the data, we predicted that the marker would get about 0.34 meters in the time frame. However, it ended up only actually going 31.9 meters. After calculating the slope and seeing the difference between the two, the difference was only 0.9966. We are oh so close to being nearly perfect about constant velocity, but why weren't we exactly? Two big things here. We didn't actually get rid of friction, nor did we get rid of any air resistance. Nor did we push the marker perfectly or track it exactly perfectly in the center of mass. These things combined could have led to there being some differences between our data and the actualness of our predictions. Overall, despite the lines having slight differences, we were able to prove that constant velocity can be observed with there are no, well, try to have no net forces acting on a system. We proved that we were able to almost nearly predict exactly how far the motion of the marker was within the time frame and compare it to the actual experiment.